So continuing with the acid-base neutralization reactions. We looked at what an acid is and what a base is. We look at this and we recognize that it's an acid because it starts with H. We look at this, we recognize it's a base because it has OH at the end. It's an ionic compound. There's some metal here and OH. And so when you have an acid and a base, you're always going to get the same type of products. You're going to get water and salt. Now this is sodium chloride, which is table salt, but any ionic compound is called a salt. Okay? Did I show you the assault rifle? Yes. Yeah. So the assault rifle is always funny. Usually this salt is aqueous, but it doesn't have to be. The net ionic equation for many acid-base reactions is the same. Question?
Yeah, I'm still kind of confused on, I know how sometimes you can cross the charges. I don't really understand when you would and when you wouldn't.
So a little confused about crossing charges to make the ionic compounds.
Yeah.
So you look at the charge on the cation and the anion. One's positive, one's negative. If they're the same number, like both 2 or both 3 or both 1, you don't have to do anything. If they are different, then you can do the crisscross thing. And it'll work most of the time.
And when you crisscross it, so does it just crisscross the charge or does it go into a coefficient?
The charge becomes a coefficient. There we go. Oh, I don't want gray. Pale yellow is better. Okay, so if we had something like sodium has a +1 charge, sulfur has a -2 charge. So we look at those two ions and we recognize we can't just put them together, so we'll crisscross. This is an unwritten 1. That becomes an unwritten 1 subscript for the sulfur. This is a 2. That becomes the subscript for the sodium. So this is Na2S nothing. Na2S. Okay, does that help? Any other questions? So when we get to the net ionic equation, what we'll find is that most of them will come down to the same net ionic equation. Hydrogen ion plus hydroxide ion forming water. The salt that is formed is usually soluble, and so those ions are just spectators. Excuse me. So the pattern for acid-base reactions is the acid plus the base gives us water plus salt. Salt meaning an ionic compound. So let's do an example. This is asking for the molecular and the net ionic equation for the reaction that occurs between aqueous H2SO4 and aqueous KOH. So first of all, we have to write down what our reactants are, and this problem is a little kinder, and it gives you the formulas, right? So H2SO4, it says aqueous, so put AQ. Remember, if the problem says include the state symbols, then you have to. A master in chemistry wants those, and it's very particular about how you put those equations in, isn't it? If I give you a question and I don't specifically say to include the state symbols, it's okay if you leave them out. That's one of those things where sometimes they're important, sometimes they aren't. But you need to know how to use them. So we're just going to practice. And then KOH, I'm leaving a little space there. You see that space? Just in case I need to put a coefficient. AQ. And then that's going to form something. So this is an acid, and this is a base. This has got a metal with OH, and this starts with H, so it's an acid. So the products are going to be water and salt. Okay? I think the best way to approach this is to think of it as just like one of those precipitation reactions where we're swapping partners. And so below this, write the ions that are contained in it. So we have H plus and SO4, 2 minus. There are 2 H's here. Okay, I've gotten a couple of people, doing homework, and they're doing stuff like this, and Mastering Chemistry is not happy with them, because that's not right. The 2 means there are 2 of those ions, but it's not a diatomic ion. It just means there's 2 of these H pluses. And the other ion is the SO4 with a 2 minus. So there's always 2 ions. Don't break this into hydrogen, sulfur, and oxygen and have 3 different ions. Only 2 different ions. So those are the ions in that one. And this one has K plus and OH minus in it. Again, 2 ions. The metal and everything else. And so we can approach this with that whole swapping partners idea. So we've got H plus and OH minus pairing up. And then we've got K plus and SO4, 2 minus pairing up. H plus and OH minus, the signs are the same, so you could just push them together. And you look at that and you're like, that's kind of funny looking. Oh, wait a minute, that's water. Oh. So let's write it the regular way. H2O. What's the state of water at room temperature? It's a liquid. And if you don't recognize that, we've got some other things we probably need to talk about too. K plus and SO4, 2 minus. This is where we need to do that crisscross thing. So this 2 becomes the subscript for the potassium. The unwritten 1 on the potassium plus 1, was that one locked? I'm sorry. It must have been unlocked and then I locked it. This unwritten 1 becomes a subscript on the sulfate. So this is going to be K2SO4. What's the state of that? How do we figure that out? Well, we need to use the solubility rules, right? In the solubility rules, one of the first rules is that potassium salts are soluble and there's no exceptions. So that would be aqueous. So there we've got the products. Question? Okay.
How do you know, whether or not it gets a positive or a negative charge, when you mix it?
Like here are the ions?
Yeah.
How do I know whether they get a positive or negative charge? Okay, the first ion is always positive, and the second ion is always negative.
Okay.
And usually what happens is the first ion is just the first letter, or the first element. So this is K, that's a metal. It's going to be an ion by itself. And we know what its charge is by looking at the periodic table. Potassium is in group 1. All of the group 1 elements form +1 ions. And then the rest of it, this is what's called a polyatomic ion. It's listed in the table. And you need to work on memorizing those guys. So this is, anybody know its name? Hydroxide ion. So hydroxide is OH minus. And at this point in chemistry, I can't really explain to you why, because it's beyond what we've talked about. So you just have to say, well, because. It's hydroxide because.
My other question was why, because you have K plus SO4 2 minus, why does the 2 jump over to the K and then nothing happens on the SO4?
Okay, so why does this 2 come down here and nothing happens to this? That's a good question. So when we're forming an ionic compound, the ions come together in a way that all the charges add up to 0. So if we put 1 potassium ion and 1 sulfate ion together, the charge overall would be -1. Right? Because this has a +1 charge, and this has a -2 charge. So if you add those together, you get -1. So what this is going to do in a compound is you're going to have 2 of the potassium ions for every 1 sulfate ion. So that when you add these charges up, you get a total of +2, and the total negative charge is -2. And so that's why there's 2 potassiums for every 1 sulfate. Because the charges, every compound is neutral. Nature doesn't let us separate charges. It just doesn't do that. You can't have a jar or a beaker full of positive ions without negative ions. It won't let you do that. We could do a lot of cool stuff if it would let us do that, but we just can't. Does that answer your question?
Yeah.
Any other questions? So I'm taking, just like we did for precipitation reactions, I'm taking the acid apart. It's going to be hydrogen ions and whatever else is left. I'm taking the base apart. It's probably going to be a metal and then hydroxide ion. And then I'm swapping the partners. And you have to have a plus with a negative. You can't have 2 positive ions together because they will repel each other. It's like magnets. You can't put the 2 wrong ends of the Brio train together. They will not stick. They'll push each other apart. That's what hydrogen and potassium would do. They're not going to stick together. So we're swapping the partners, and then we're looking at the charges to figure out what the formula is. Then we need to balance the equation. So over here, there are 2 hydrogens. And this gets a little complicated because there's 2 hydrogens here and there's 1 there. And then there's hydrogens over here, right? So let's maybe not start with the hydrogens because they're kind of all over the place and that looks like it might be messy. Here, maybe let's start with potassium instead. We have 1 potassium on this side of the arrow, but we have 2 on that side of the arrow. So that means we need to put a coefficient of 2 in front of the KOH. Now we have 2 potassiums here and 2 there. This sulfate stayed together as a unit, so we can balance that as a unit. There's 1 sulfate ion here, and there's 1 sulfate ion over there. And then we have to look at what's left. So here there's 2 hydrogens from this one, and there's 2 hydrogens here. That's a total of 4. And over here we only have 2 hydrogens. So we need to put a 2 in front of the H2O. And that's going to take care of the remaining oxygens. Ignoring oxygen that's in the sulfate, we've got 2 oxygens here and 2 oxygens here. If you don't like balancing sulfate as a unit, you can balance it as sulfur and oxygen, and it will come out fine. So here we've got 1 sulfur and 1 sulfur. Here's 4 oxygens plus 2, 6 oxygens on that side, 4 plus 2, 6 oxygens on that side. Okay? So that's writing the molecular equation and balancing it. Now I'm going to erase some of my scribblings here. Oh, these guys over here too. It also wants us to write the net ionic equation. When we learned about net ionic equations, the thing we did before that was to write the complete ionic equation, right, showing all of the ions. This is an aqueous compound. It gets separated into ions. How many hydrogen ions are in 1 unit of this? 2, right? So this would be 2 of those and 1 sulfate. This, now that we've got a coefficient of 2 in front of it, that means there would be 2 potassium ions and 2 hydroxide ions from that one. I'm kind of writing just a scribbly complete ionic equation here. Now this one, see that state symbol L? That's a liquid. We only separate into ions aqueous compounds. Liquids, solids, gases, you just write them as they are. So we don't want this shown as ions. We want this shown as water, and there's two of them. And then we're looking at this one. This one is also aqueous. There are 2 potassium ions, so I'm going to put a 2 here. And so what I've done is I've taken my scribblings that were helping me figure out the products, and I've turned them into scribblings to help me figure out what the ionic equation is going to be. So let's maybe throw a different color in here. So that would have, can you see that? That's not a good color. Let's try a different color. So that would be plus and plus and plus that one, and that would form these guys over here. And if we wrote that all out neatly, that would be our complete ionic equation. The net ionic equation, we cross off the spectators. Spectators are the ones that come and watch but don't participate. What are the spectators here? Potassium and sulfate. See, there's 2 potassium ions over here, and there's 2 potassium ions over there. Nothing happened to the potassium. It was in solution before, and it's in solution after the reaction. So I'm just going to cross those off. And then sulfate. Here we've got 1 sulfate ion and 1 sulfate ion. Sulfate did not participate in the reaction. So I eliminate the spectators, and then I take what's left and write it down. Well, what I've got left is 2 hydrogen ions. Since I have more room, I'm going to put my state symbols back in. And I have 2 hydroxide ions. And on the right side, what I have left is 2 water molecules. What's funny about that equation? The coefficients. It's 2, 2, and 2. Do we really need all those 2's for it to be balanced? No. So we can simplify that by dividing all the coefficients by 2. It's really just one of each, isn't it? So the net ionic equation is H plus OH minus forms water. That is the net ionic equation for almost all of the acid-base neutralization reactions that we'll see in this class. Yes, question?
On the ionic and the complete and net, do you have to include the plus and minus symbol, the charges?
Yes. On the net ionic and the complete ionic equation, you have to include the charges. We do not include charges when we write the formula for the compound. But when we write the ions separately, we have to include their charges. It's a good question. Any other questions? And sometimes, yes?
The H2O, why didn't you break that down?
Why didn't I break H2O into ions? Because it's a liquid. So it being a liquid, solid, or gas tells us that it's not separated into ions. Only things that have AQ will be separated. So if it says AQ, break it into ions. If it doesn't say AQ, just copy it down as it is. Any other questions? This is one of those things where you can watch me do it, and you may say, oh, yeah, okay, I see. And then you go to do it on the Master in Chemistry, and you're like, oh, wait a minute. Because you think you got it right, and Master in Chemistry says, nope, try again. You have to practice this. Okay, so practice it and ask questions. I've had several people over the weekend asking me questions about the net ionic equations, and that's good, okay, to get those things cleared up.